Talked about conservative transport, where we can use those closed form solutions and also our simple idea of those closed form solutions if Peclet number is large enough. And we end up having some observation for flow through the saturated zone, either for a conservative tracer, where we can kind of evaluate the length traveled if Peclet number is big enough as the product of velocity and time divided by retardation. If retardation is equal to 1, then we get the conservative value. If retardation is larger than 1, we saw last time that it can go up between 1 and 30 or so, then this would be 30 times backwards, retarded by a factor of 30. And as a function of the way that we divide through the diffusion coefficient by retardation coefficient to reduce it, it essentially becomes a sharper front. If we look at what this looks like in terms of the downstream behaviors, then these two behaviors we can also get in terms of the residence time distribution, in terms of the time taken for the conservative front to arrive. The time taken for the non-conservative front to arrive is longer because it's delayed, and it's delayed according to these properties. We can calculate these properties from natural gradient transport tests. That would be unusual that we'd have those data, but we can also get the retardation factor if we know what KD is, and we can estimate KD as a function of different characteristics, either from solubility or oxygenol water partition coefficients, as we saw last time. So we can do that all in the subsurface, and this is all in the groundwater regime, to be able to say how quickly something is going to travel downstream to get to us at some particular location. We know how to do that. So we also know that if we have a spill on the surface or in an underground storage tank, it might be above the water table. And if that is above the water table, then the processes by which transport will occur are somewhat different. We know that the chimney, as it goes down through here, will go through the vadose zone, and there'll be some off-gassing through that. If the source is present within here, then we might want to understand something about the mechanisms by which it can be transported in the predominantly gas-filled pore space of the vadose zone. So the last thing that we'll deal with in terms of transport processes is to be able to understand something about that. And so that brings us to this final topic, which I guess is this. That's kind of summarized here, and that is transport in the vadose zone. And I guess we went through a lot of stuff last time. I think we've got to go through a lot of stuff this time, so I better get my act together. And so what we're going to look at is mechanisms by which transport can occur, and we'll find out that we can understand behavior by diffusion. We have to understand something about partitioning, and partitioning between vapor and water. And as a function of this, we know that if partitioning occurs, and solid, I guess, for that matter. So we could have the DNAPL, some of it will vaporize, some of it will be dissolved in water, and some of it will sorb onto the solid. And so we saw last time that if material is sorbed onto the solid, we get retardation. And so maybe our understanding of all of these three things above means that we can also define retardation as a function of these partitioning behaviors. And so if we look at that, that gives us an ability to be able to say about how quickly diffusion may occur. And then we'll look at a second mechanism by which it can be transported, and that is by advection in the liquid phase. And so this is the basic idea of what we're looking at. And so you have some kind of spill, So it goes into the subsurface. This subsurface could be partly DNAPL saturated, partly air saturated, partly water saturated. It could, of course, be the column that goes all the way down to the lenses of DNAPL that exist within the groundwater zone as well, right? For that matter. So it's something that's going to be ubiquitous. Any spill on the surface has to make its way probably across the vadose zone, since the vadose zone is ubiquitously present. And so the mechanisms you can imagine that it can travel by would be by diffusion, Fick's law. This would be Fick's law. Q equals d dc dx, being driven by a concentration gradient. It could be driven by flow, because these vapors are typically denser than air, and so they'll sink. And if they sink to the vadose zone, then they will contact the vadose zone and may be dissolved by dissolution into groundwater, as we've talked about. And if they're dissolved in water, then they can also be transported down gradient to some compliance location. The stuff that diffuses, you could off-gas and you lose some to the to the surface. You could also imagine that rainfall will potentially pick up some of this stuff and transport it down by advecting it down here by the motion of the water. So that's the final mechanism that we said we'd look at in terms of aqueous advection. So those are the kinds of mechanisms that we'll think about. They're kind of shown in cartoon form here. This is diffusion, and this is aqueous advection, as we've just described. This is driven by Fick's law, which will drive the transport on concentration gradients. This is a moderately effective way of moving the vapors around, but not as effective as perhaps dissolving them in water and transporting them to the vadose zone, to the groundwater zone. And so that's why this is an important one for us to look at. Dense vapor transport might also be important, but certainly not as important as this. These are the major two things in terms of the masses that are transported that we need to be able to accommodate. So we'll deal with them both in sequence. And so we need to be able to define some equations that describe this. We've seen all the equations we need to see, so let's just talk about them I'm going to jump that. Let's just talk about them in terms of what we know. So Fick's first law says that the mass flux of a component is given by the concentration gradient concentration changed over length, which is the concentration gradient, a diffusion coefficient, the star meaning effective, and phi g being the volumetric gas content of the porous medium. And that is because if it's traveling by diffusion in air, the only part of the medium through which it can be transported in air is the part that's air-filled. And so that's why this comes before it. I suppose, strictly speaking, it should have a negative sign there, because the diffusion occurs in the opposite direction of the positive gradient. And what we usually do is we combine this Fick's first law with Fick's second law, which is just mass in minus mass out equals rate of accumulation. So accumulation on the left-hand side here, mass rate in minus mass rate out on the right-hand side. C sub g is a concentration in gaseous form, and this disappears when you do that as a consequence. And so this is the expression that we'll use to define diffusion in the system. It's not any different from the system that we looked at before, which you might remember had we explained behavior in terms of length, or radius if you like, and concentration. Perhaps I should change it into a different color. And if you start off with concentration of a drop of ink, if you like, in milk, maybe that was the analog that I mentioned, is that at time t0, it might look like this. At time t1, it looks like this. And time t infinity, it looks like this. And this is just the normal, the Gaussian distribution curve, the normal probability distribution happens to be. And it's a solution to this equation, except when we solved this equation before, the term on the left-hand side was 1. And so the only difference here is that now we have this retardation coefficient, which we haven't yet defined, which we could divide through on both sides. So this now really is 1. It's exactly the same as the expression we had for this, except that now we're working with a effective diffusion coefficient that now is reduced for an amount because it has retardation in it. And so if you think about what that might make this look like, then you'd think that it would look like this. So if you take half of this profile down the middle, the right half, I suppose, in this particular case, then that's exactly what you kind of have here. If it's not retarded, then it will, at some particular time, t1, it will look like this. The meaning of the retardation coefficient is that it's traveled that percentage less far in that given time. If r is equal to 1, then this is the value, dg over 1. If r is equal to 2, then it will have traveled half as far in a given time. That's physically the meaning of the retardation. So we haven't really said what retardation factor is yet for this, for diffusive fluid transport, but that's what we need to be able to do. So if we want to be able to define this diffusive transport, I suppose we need to figure out two things. We need to figure out what the effective diffusion coefficient is, and we need to figure out exactly what the retardation coefficient is. And if we can do that, then we have everything we need to be able to solve these problems using the equations we already have. So the effective diffusion coefficient relates to the fact that if you have a cigarette in air, then the rate at which the odor of that migrates to you is the diffusion coefficient in air. If you happen to be in a porous medium, instead of going directly between me and you, if I'm the cigar smoker, then it has to go through the tortuous path, which is the porous medium. And so just as in the same way we modified the aqueous diffusion coefficient for tortuosity, we have to do the same for porous medium. And so we can get that merely by defining a term which scales it, which we'll call the tortuosity. And there are a variety of ways to do this. The most broadly used is this equation by Millington and Quirk, which merely defines tortuosity, or the effective tortuosity, as a function of the volumetric gas content to the total content. So remember that the theta G is the vol gas content. Theta W would be the volumetric water content. And if you only have two components, if you add those together, you get porosity, or in this case, the total phi lowercase t. So this is the part of the portion that is gas filled. This is the portion of the void space which is gas and water, liquid filled by definition. And so if you do that, then we can scale the magnitudes of this diffusion coefficient relative to the magnitudes of the volumetric gas content. And we know something about how volumetric gas content should change as a function of depth. This is our saturation versus depth curve, or it could be PC, I guess, but it's depth. We know that at the water table, it should be ostensibly 100% water saturated. Above the water table in the vadose zone, this should be residual non-wetting saturation. So this would be, I guess this amount here would be what we referred to as SNW0, right? Irreducible non-wetting saturation. Non-wetting fluid is the water. And I guess just to be clear, volumetric moisture contents are equal to porosity times the saturation, right, by definition. Saturation is 1, then it's fully filled with water, and this is the same as porosity. And so as you go above the water table, the gas content increases up to some maximum amount. And so if you do that here, this is just a contrived example to be able to go through it and calculate what the gas, if the volumetric gas content is 25%, if the porosity, the porosity of 35%, so this is porosity also. Then if you just plug and chug by putting in the gas content, the total porosity to get tau, and if you multiply by the value of the diffusion coefficient, which you get from a mechanical engineering textbook, which is apparently 2.6 times 10 to the minus 6 meters squared per second. Diffusion coefficient for TCE in air, in the room. You multiply it by the effective tortuosity, and you get a value of the gaseous gas diffusion coefficient, which is quite high higher up, quite low lower down. This is 10 to the minus 8, 10 to the minus 6. And then when you go into water, it's not this value at all, because you're not diffusing in air anymore, you're diffusing purely in water. And the diffusion coefficient is what we've called D star, we just called it D star in part 3. And it's something like 2 times 10 to the minus 9 meters squared per second. And so these values change from relatively high in air to relatively low. It's a third of this magnitude in water. And just based on these individual components. So that's the first part we need. So we've said something about figuring out exactly what this top term is. We might also like to say something about retardation. So the second part is to say something about that. So retardation results from, it was the dissolved component in water partitioning onto the solid. But if we're talking about the vadose zone, we have water and solid, as we did in the saturated groundwater zone, but we have air as well. And so what we need to use is Henry's law, which defines the partitioning between the gas and the water, equilibrium partitioning. And so we can define this non-dimensional Henry's law coefficient, which is just the ratio of the equilibrium concentration that is happy within the gas relative to in the water, if these are both in the same units. So it's non-dimensional. But unfortunately, Henry's law coefficient is usually defined in these more convoluted thermodynamic terms. And H prime is the one that you usually pick up in a text, which relates the partial pressure in air relative to the concentration dissolved in the fluid, and through this rather strangely termed Henry's law coefficient, H prime. So this is what you pull out of a textbook. This is what we'll ultimately try and use in this class. And so this just results from the fact that you're relating a solubility, mass per unit volume, to a partial pressure. And so the units have to be strange to accommodate that. And the units therefore are in atmospheres, meters cubed per mole. A concentration in moles per meters cubed, a partial pressure in terms of atmospheres, and the coefficient that links these together has to be dimensionally coefficient. And so between the water and the gas in the vadose zone, we'd expect Henry's law to define that partitioning, and we'd like to be able to define it in a slightly different, simpler way, and we will. And between the water and the solid, the solubility dissolved in water will partition onto the solid exactly conforming to our distribution coefficient. And that if we can calculate our distribution coefficient, then we can calculate what is it? KD is equal to dc star over dc, something like that. That was our term, our definition of distribution coefficient. So this is concentration on the solid, concentration in the water, and the ratio of those two at equilibrium is just this magnitude. Sometimes we can get it by octanol organic carbon partition coefficients and fractions of organic carbon, but this is the term that we need. So the two mechanisms are water and air equilibrium and water and solid equilibrium. And so we can define the retardation coefficient without deriving it as due to those two components. And the basic idea is that in the porous medium you have solid completely surrounded by a monolayer of water, and then you have gas with air within the pore space. And so you can think about the solubility of the compound in water, that being in equilibrium with the air on one side, and you can think about the solubility dissolved in water, and that also having to be in equilibrium with the concentration sorbed onto the solid. And so we can think about that kind of three-stage process, that the part that's in the water has to be in equilibrium with the solid, and it has to be also in equilibrium with the gas. And so that's why this term here has an extra term. So the partitioning between water and the gas is given by this term. Looks new to us. The part which is in equilibrium between the water and the solid is this term. Looks kind of similar, right? Except for this term here. If there is no gas in the system, then we lose this. This goes to 0. But if there is gas, we have to account for it. And we have 1. So in aqueous behavior, we have this plus this term here. If we have air in the system, then we have this additional term, and we also have the impact of this. So that's how we can calculate retardation factor, if we know exactly what the value of this dimensionless Henry's law coefficient is. Of course, we still need to know the magnitude of distribution coefficient. I think I've always used uppercase KD for it. And so we just need to be able to figure out exactly what this Henry's law coefficient is, which is the ratio of the equilibrium concentrations in the air and in the water that contacts the air. A quick example, just using some contrived results. We don't know yet what this non-dimensional unit might be that links gaseous and aqueous concentrations, but take it on trust that it's of the order of 0.3. So if we know what the magnitude of the organic partition coefficient is in something, we could calculate that Kd is equal to the fraction of organic carbon multiplied through by KOC. If we know what the fractions of organic carbon are, then we can calculate exactly what the magnitude of this retardation factor might be. And so if we do it for two cases, and the two cases are if the fraction of organic carbon is only equal to 0.01. We said that we shouldn't be using it at such low concentrations of carbon, but let's use it anyway. And if the fraction of organic carbon is 1%, so 0.01 decimal is the magnitude. The part that sorbs due to the gas phase is equal to this. If it's volumetric moisture content of 10%, 25% gas content, just like the previous example we did. Bulk density of the aquifer is 1,650 kilograms per cubic meter, which is what this is. Then the sorption, the effect of retardation on in the gas phase is equal to 1.3. So we have 1 plus 1.3. It doesn't change with the amount of organic carbon because you'd expect it not to influence the equilibrium retardation just in the gas phase. If we look at the effect of the part that's sorbed onto the solid, this part here, which is this, then clearly this is a function of the magnitude of Kd, and Kd also is a function of the organic fraction. And so if we do the calculation for this term, also including the magnitude of Henry's law coefficient, which is 0.3, then the part that's sorbed onto the solid is either 0.27, or if it's 100 times the organic carbon concentration, it's 100 times that. And so if you look at adding these together, you end up with these two numbers. So the retardation factor can be large. Again, we saw last time it could be between 1 and 30. Here it is between those numbers. By far the biggest impact on this, though, is the part that's sorbed onto the solid and not the part that's sorbed into the gaseous concentration. So that's kind of just an example to be able to illustrate that point. The other thing that comes out of this is also that for different compounds, you may end up with different rates of retardation. And so you know that when we were talking about retardation, we looked at the relative rates of concentration traveling with distance. And just for diffusion, we said that length is equal to diffusion coefficient over time times retardation. Is that right? I can't remember the units are. Well, I don't have this. Length over r. Length over r. So the distance doesn't matter particularly. But the idea is that it would be, actually it's the opposite, isn't it? It's r, it has to be r on the bottom. The length traveled is going to be reduced by r. So if r is equal to 1, you'll travel this far. If r is equal to 2, or maybe 3 in this particular case, you'll travel this third as far in the time. So the meaning of this is kind of the same in aqueous form as in gas form. This is the one that we used in parts 4.1 and 4.2. So on last Thursday and on Tuesday, we used this in the saturated zone, and this is in the vadose zone. So depending on the magnitudes of what these retardation coefficients are, they will determine how slowly the plumes migrate between upstream and downstream. And so you could imagine a plume that is present both within the vadose zone and is happily diffusing away, and in the vadose and in the groundwater zone that is diffusing by Fickian diffusion in a static groundwater regime. And you can look at when they would arrive at monitoring locations that are downstream. The order that they'll arrive downstream will be in progression of the retardation coefficients. So if the retardation coefficient is 1, it'll arrive earliest. The compound that has a retardation coefficient of 2 will arrive next, and the one that has a coefficient of 3 will then arrive. And so what you could do as a thought exercise, look at 3 different components, look at the magnitudes of their aqueous solid partition coefficients, their Henry's law coefficient, to be able to calculate each of these retardation coefficients from these 2 equations, and then go through and calculate the retardation coefficient for the aqueous component and the retardation coefficient for gas-borne components in the vadose zone, right? So this one here would be traveling in the vadose zone, this one here would be traveling in the saturated groundwater zone. And if you look at the relative order of those retardation coefficients, the smallest one is the first arrival, the next largest one is the second arrival, and the next largest one is the third arrival. So in the groundwater zone, you'd expect them to arrive in the order of first, second, and third. But in the the gas zone, this is gas zone, this is G, not groundwater, gas. In the aqueous zone, below the water table, the arrival would be first, second, so this is least, so I did the wrong one. This is this one, and this one. And if you look at the retardation in the aqueous zone, the fastest one is this one, the second fastest is this one, and the third fastest is this one. And so, as you cross-correlate this, the first arrivals are the same compound. The second one to arrive in the groundwater is TCE, but the second one to arrive in the Vado zone is trichloroethane. So they arrive in a different order. And so that can happen just as a function of the different magnitudes of the values of KD and the different magnitudes of the value of the Henry's law coefficient that we have to deal with. So maybe a quirk that they arrive at different rates. So you can also look at the magnitudes of the Henry's law coefficient. So if you have it only traveling within the Vado zone, so by gaseous transport, you could try and predict the rates at which compounds would travel if you did an experiment. And this is an experiment in a relatively contained environment. A test cell which is 10 meters by 10 meters by 3 meters deep, which is just really a hole in the ground, but it's a hole in the ground which is lined in concrete, in which you can build an aquifer, and in which you build an aquifer of sand, and into that aquifer you place a source by injecting a gaseous content of either methane, butane, or trichloroethylene. Methane, butane, or TCE. And then looking at how far it has traveled after a day on the left-hand side, or after 3 days on the right-hand side. And you do it by using these little ports, which are just sampling capillary tubes, which you can suck gas out of to be able to see what the concentration is. And if you do that for all these ports at 24 hours, you can have a contour plot of the distribution of these different compounds. And so clearly methane and butane have diffused quite far, and TCE has traveled less far. And so you can see whether that corresponds, what controls that, in terms of the Henry's law coefficients. And if you evaluate the Henry's law coefficients for methane and butane, you find they're of the same order of magnitude, quite high, and therefore have quite high diffusion rates. And TCE is almost is an order of magnitude lower, right? 0.4 versus 8. And so this is the one that travels less far. And the reason for that is that it's traveling less far because it's more heavily retarded, because retardation factor is proportional to the reciprocal of this value of Henry's law coefficient. And so it makes sense to be that the value of retardation coefficient that we're using actually gives you some defensible behaviors that you observe in the subsurface, so that one sample which has a lower Henry's law coefficient and therefore in gaseous form is more heavily retarded as a result of a low constant results in traveling more slowly. And so that's the physical meaning of retardation. So if we can use this value of retardation coefficient to define our behavior, we still have to figure out exactly how we define it. And it's relatively straightforward. This is the term that we want, which is just a mere ratio of gaseous and waterborne concentrations. Both of these are in the same units, so this has no units. And we can check, of course, the dimensional homogeneity of this. No units, this is a ratio of percentages. This has no units. And we talked about this term here having no units before. So this clearly must have no units if it's supposed to contribute to this. So we know that it has to have no units. And so how do we get it from the magnitude that you might get out of a reference text? This is the magnitude you get out of a reference text. It would be defined in these strange units that we talked about, atmospheres, meters cubed per mole, or whatever. And it's defined in terms of a pressure and a concentration. A pressure in terms of a pressure, and a concentration in moles per meter cubed. So I guess the units of this must be an atmosphere per mole per cubic meter, by definition. If we use the pressure to be defined by the ideal gas law, pressure is equal to density, absolute temperature, universal gas constant, and the molar mass of the gas. This is the universal gas constant, same value for every compound, and we substitute it in here. We substitute the value of concentration in moles per cubic meter. We end up with this equation on the bottom. If we divide this equation up on the bottom so that we merely take this value here and rewrite it as it is here, then immediately we recognize that this value here is equal to the ratio of the two concentrations. The density of the gas divided by its molar weight is the mass per unit volume. So that's a concentration. So this term here is the concentration of gas in the gas, and the concentration in water is on the bottom. So in other words, this term here by definition has to be our value of non-dimensional Henry's law coefficient. So the punchline, I suppose, is that you can get the value of the parameter we want just by taking the textbook value and dividing it through by the universal gas constant and the temperature that you find yourself at in terms of degrees Kelvin. And so a quick example of that is the universal gas constant. Temperature, if it's 20 degrees centigrade, is 293 Kelvin. And the value of the textbook magnitude, which is 9.1 times 10 to the minus 3 atmosphere meters cubed per mole. All the units work out, and indeed you end up with a value somewhat similar to the one that we used before, right, which was 0.3, I think. So that's perhaps the last thing you need. So this will be the value you typically get in a reference text, and this is the value that we want to be able to use in our work. Won't worry about that, we've already done it. Not going to worry about that as well. I will just say something quickly about Raoult's law. We only talked about it last time for the first time. So remember, we talked about the idea that if you have TCE dissolved in water, its equilibrium solubility is 1060 milligrams per liter. But if it's competing with another compound, which is also present, then it has to compete to be dissolved in water, and the concentrations will actually be less than their pure phase solubilities. And merely you modify them by multiplying through by their molar fraction. So you can do that in the same way that you would do here. The effective concentration you'd have within the gaseous form is going to be the molar concentration fraction that you have present dissolved in water, multiplied by the concentration, equilibrium concentration, the concentration in air. And so in the same way that you're soluble or vaporizing in air, you're competing with the amount that's already in air. So the amount of effective concentration of gas relative to this would be the pure phase concentration. Concentration but in air, I guess this time, not in water. And so you can calculate what that would mean. And so we have all the things we need really to be able to evaluate how far diffusion would take us. So if I don't want to give you whiplash, but remember we were talking about two fundamental systems. First was by diffusion. And so we thought we could define this diffusion by the diffusion equation, which was something like, something like this. Normal probability distribution. It depends on our effective diffusion coefficient, which is within the pore space, so we have to modify it for that. And it's affected by the retardation, so we have to figure out exactly what this magnitude is, and we know what both of those magnitudes are. And so this describes the behavior, how quickly it would spread outwards by a stagnant flow field here. So the air is not moving here, this is just traveling as an odor would within a room, so that you smell it at some time later as it diffuses towards you. The other mechanism that is much more impressive in terms of being able to carry components, would be by waterborne advection. And so the idea is if you have rainfall occurring on the surface, that rainfall will travel down through the patch of material that you have, it will dissolve it, and then it will carry it down to the water table, and then at the water table it will carry it off in the same way that we've talked about by transport in the groundwater zone. So that's the final thing that we'll perhaps spend a few minutes talking about. And it's relatively straightforward because it borrows on all the concepts that we've worked on before. And so here's just a very brief example explaining it. It's modeled on an experiment that was done at Borden, the same place that we saw the separation between the plumes in the natural gradient transport experiment. Happens to be a different experiment that's putting something in the ground and then raining on top of it so that the rain carries it down to the groundwater table, and then looking at the plume that develops as it's carried away from there. And so how do we determine what the loading is that will end up onto the water table as a function of rainfall? If I can draw a cloud here. Rainfall raining on this, some infiltration on the surface, which gets carried down here, picks up dissolved components at a maximum level here, and then carries that mass down to the water table. We'd like to be able to calculate the mass in kilograms per meter squared per year, I suppose, right? How much of this dissolved mass is going to come down here? So how can we rationalize that largely on the things that we know? So what we could do is we have this. We could calculate how long it would take for the water to get from infiltrating here to going through this region, 2.5 meter, at half a meter depth. And so once it arrives here, then the rain, if you think about it, in this material here, we'd have a profile. If you think about the saturation versus elevation distribution, it would look something like this, right? This is saturation of water, 0, 1. This would be the amount of water that is present there. In the tension saturated zone, this is the amount of water that is there. So if you imagine that rainfall is occurring and the system is in equilibrium, then this saturation to water isn't really going to change in the upper region. And so as this rainfall comes in at some infiltration rate of half a meter a year, 45 centimeters per year, it is going to travel down through the part of the vadose zone which is already water saturated. It's not going to change this saturation to some other magnitude, it's just going to fill up this region here. So what we'd like to calculate is how quickly it moves through the vadose zone if it's only traveling in the part of the aquifer which is originally water-filled, and it's water-filled at 10% of the volume of the aquifer. And so we can calculate that very simply, that the advective velocity is going to be the Darcy velocity, the infiltration rate, right? This is the velocity of water over the total surface, which is the same as the Darcy velocity. This is the infiltration rate, 45 centimeters a year. It's traveling only through the saturated portion of the aquifer, which is 10% of the cross-sectional area. And so if this is 10%, the advective velocity is 10 times the infiltration rate. So the infiltration rate is actually, the velocity here is going to be 4.5 meters per year, right? Just by this simple calculation. And so if we want to get from this location, which is 2.5 meters above the water table, to the water table, it's going to travel 4.5 meters in a year, so it's going to travel 2.5 meters in about half a year. And so we can calculate exactly what that magnitude is. This assumes no retardation. If you thought it was being retarded, then I guess the travel time would be reduced by that factor. So if retarded, I guess, then travels times r slower. So if it was retardation factor of 2, it would travel 2.25 meters a year. If it was a retardation factor of 4, it would travel 1.125 meters a year, etc. You can work that out. And so if you know the retardation factor, you can calculate that out. But the other question we want to know is, what is the loading that occurs on this surface? So how much mass dissolved in the liquid comes across this surface? Well, the mass rate is going to be equal to the area times the Darcy velocity times the solubility. And so the mass rate we can calculate if we know the area, we know the Darcy velocity and the solubility. So solubility here we're calling, I think, below the concentration in water, CW. And so this Darcy velocity is equal to times the volumetric moisture content. It's just the product of these. And so that's because advective velocity is equal to Darcy velocity that's where this term comes from. So in other words, the mass loading is going to be the Darcy velocity, which is this term, multiplied by the solubility, which is this term. This is just a velocity multiplied by solubility times an area. So this area here is just unit area. So this is the volumetric moisture content is 10%. The advective velocity is 4.5 meters a year. These two together, of course, would be 0.45. Meters a year. The same as the infiltration magnitude, 45 centimeters a year. And this would be the concentration of the dissolved in water. It was 1060 or 1100 milligrams per liter. And so if you do the math, you end up with a magnitude of something like 450, half a kilogram per year in this particular system. So the amount that's being delivered to this surface is half a kilogram per year, that order. So I don't know whether that's big or small, but it's a magnitude you can calculate for sure. Of course, the retardation factor doesn't come into that, because as soon as the front has reached there, then it's there. So it just takes a bit longer to get there, but once it's there, it will deliver itself. It won't reduce the concentration, but it will take longer to get there in the first place. And so you can calculate that. You can do more use more sophisticated models to calculate this. These are results of some models which do this, and they're just shown here, just for example. It's kind of the last slide we'll look at. And it's merely to look at the case where you cover the ground surface with a membrane. So you have this source that's present within the surface in both of these cases. One of these is open to the rainfall. One of these is closed to the rainfall. Rainfall is being forced off and off to the side. So there's no infiltration that occurs here. You can look at the concentrations of the vapor away from this. They start high close to the system, and they get progressively lower outside. But as a function of these concentrations, you could calculate, if you have infiltration at 45 centimeters a year, you could calculate what the loading was onto the groundwater table and integrate it over the full length of this thing here. So presumably the amount would be highest here, and it would taper off as you go outside. So these would be the magnitudes of the mass loading. So the red arrows are the mass loading, not the flow loading. And it turns out in this case that if you do that, for this example, you get 5 kilograms occurring after 6 months. I'm not sure if that's 5 kilograms, I guess it's after 6 months. And more than that after a full year. Perhaps different results from what we have. If you cover it with a membrane, then because all of the fluid that would carry it is being diverted off to the side, all that's going into the groundwater is what's contacting it through contact, if you like, by diffusion. And the results are that you've reduced it by more than an order of magnitude, right? 0.35 kilograms and 3 kilograms versus 15. And so, not difficult to suggest that the mechanism by transporting this by advection that we talked about is perhaps much more effective than just by diffusion. This would be diffusion alone, the first mechanism we talked about. The loading is finite, but it's relatively low. If you look at diffusion and advection working together, then by the loading is an order of magnitude larger. And so the loading that we calculated doing this is exactly that advective loading. They're not quite the same. Well, I guess this is per unit area. So this is per square meter. And so this is total mass. And so it means that the areas here would have to be something like 10 square meters, quite large. So 10 square meters would be 3 by 3, which would be 1.5 by 1.5. I can't see the units here. So 1.5 meters, if this is 6 meters, is only this far out. This is 1.5 meters. This is 6 meters. So 1.5 meters here, 1.5 meters here. So this edge dimension would equal 3 meters. Don't know why I'm drawing with my finger. If this is 3 by 3, this is approximately equal to 10 meters squared. And presumably that's one reason why this magnitude here is not 0.5 kilograms per square meter, but 5 kilograms. If it's 10 square meters. So I think the results do make sense. They're congruent with each other. But you can diminish this magnitude by an order of magnitude just by putting a membrane on the surface, a sheet of plastic that diverts the fluid instead of going directly down through this, forces it to be only diffusion that's occurring. And that's it. So I think we've made all the points that I wanted to make in this. So we've talked about methods of transport. We've talked about how to define those in terms of the geometries. We've seen that this is a small loading potentially relative to advection, and therefore we should probably concentrate on this. This also points to the fact that if we want to quickly reduce the impacts of this, one very quick way to do that is just to divert the rainfall off to the sides so that it doesn't go through the contaminated portion, and be able to define that. The model we looked at for these last results is a model that also deals with dense vapor migration by these vapors being denser than air and therefore also sinking down by advection. So I guess this plus infiltration would give the maximum loading, because it would give diffusion which was faster than this case, because it would be accelerated by the fact that the dense vapors would fall under their own density, and they would be a more efficient transport mechanism than just diffusion alone. Advection is always much more effective than diffusion. In this particular case, the advection is driven by the negative buoyancy of the vapors. In this case, the advection is driven by the infiltration of water and the dissolution in the water arriving at the water table. So they're just a mixture of different mechanisms. So that's it. So we've talked about conservative transport, we've talked about non-conservative transport, both in the groundwater saturated zone. Those are 3 and 4. And we finally closed it out by talking about transport within the vadose zone and looking at both conservative and non-conservative transport by virtue of the fact that we've talked about retardation. We talked about how to define retardation. We've talked about the importance of advection in increasing those magnitudes. So now, since we've talked about all the transport mechanisms, I guess we've laid the ground rules to be able to say, 1, how stuff gets in there, 2, how stuff migrates, we know that, and now 3, how we can use our knowledge of these mechanisms to maybe remediate these systems. So that's kind of the logical progression. Gets into place by accident. Once it's in place, it gets moved around by movement of the water table, dissolution, movement of the water table, and volatilization. We know what those behaviors are for these systems we've looked at as conservative and non-conservative transport in the saturated zone, and conservative and non-conservative transport in the vadose zone. And so now we have a chance of being able to use that knowledge of the motion or lack of motion of these fluids in the subsurface to be able to say, in a mechanistic way, how successful we might be if we try and suck it out, if we try and dissolve it out, if we try and heat it up and vaporize it out. We have the basis to be able to make some value judgments as to how effective each of those mechanisms might be and where they might be applicable in low permeability materials like clays or high permeability materials like sands. And so it turns out that as you start thinking about your remediation methods, I don't know that you'll necessarily go to the notes in this class, but there's not a bad matrix that looks at things like depth versus permeability. So low permeabilities, which would be clays, high permeabilities, which would be sands, and all the different remediation methods that you'll look at or be exposed to fit within this matrix as to their applicability. So some only work at shallow access, some work only some methods work for deep access, some methods only work for low permeability materials like electroosmosis, some methods like soil vapor extraction only work where permeabilities are high. And so now that we know something about the mechanisms by which these behaviors are regulated, we can look at the material properties that might impact their behavior. And the material properties, the most important one we can think of is permeability. And permeability for 2 reasons. One, if it's low permeability, we can't get fluids in to flush it out. very easily. And also, if the permeability is low, it means that the capillaries are very small, and the resistance to sucking it out by trying to suck out the free phase is very slow as well. Okay, is at the end. And so this isn't a bad chart to be able to think about in terms of the remediation stuff you'll talk about. Okay, so that's it.